What's up, everybody? You guys are welcome to another exciting of our data analysis class. In today's episode, we are going to be talking about one of the nice and amazing machine learning algorithms, which is decision trees. So without any further delay, let's just dive right into it, right? Let me just go ahead and visualize things. For example, we covered logistic regression in our previous classes. Let's say, for example, if you did it like this, and let's say you have some, let's say for instance, you have customers age, let's say for example 10, 20, 30, and 40, and their likelihood of making a purchase are between 0 to 0.5 and then to 1. And let's say you have some of your data points like this. You have some of your data points like this, and in logistic regression, which is LR, you can just go ahead and simply draw your sigmoid function like this, and then you can have your decision boundaries around here, and everything is going to fit perfectly fine. But let's say, for example, this is just a very nice decision boundary. But let's say, for instance, let's say you have something like this. Let's say, for example, you have something like this, and you have some many data points like this, some random data points like this, and then maybe another data point like this. You have so many random data points laying around, and then another data point like this, right? Okay, I think it's okay, right? Okay, let's just add some few columns, right? So let's say you have so many data points like this laying around, and if you take a look at this, it's a bit complex for you to have a nice decision boundary out of this data set. For example, if it's something like this, if it's something like this, you can easily draw your linear regression best fit line, and then you're good to go, right? But if it's something like this, it's actually a bit complex to draw your linear regression line like this, and then split your data and find a best fit line. So, but with decision tree, what decision tree allows you to do, it allows you to have so many decision boundaries. Like, for example, it can allow you to split your data like this, right? And you can split like this, right? And then another split way, you can have another split like this, right? So this type of problem is where decision tree shines a lot. So without any further delay, let's just dive right into it. So let me just go ahead and highlight everything and then delete it, so that we can go ahead and see some examples, right? Let me see how I can quickly delete this. Cool. Wonderful. So without any further ado, let's just dive right into it. So actually, what is a decision tree? Before you even dive into our algorithms, what is actually a decision tree? Decision tree is actually very simple. It's a machine learning algorithm or machine learning model that looks like a flowchart, right? Basically, it looks like a flowchart. So for example, let's say we have student data, and then you want to make some predictions. Okay, let me just go ahead and draw the node. For example, let's say you have a question like study hours, and then you want to cycle it. So this is the first node, and it's actually referred to as the root node. And then let's say you have some few questions that you want to ask, right? Some few decisions that you want to make. Let's say, for example, you want to ask study hours. Is study hours greater than 5 hours? If study hours is greater than 5 hours, if that is a yes, then you come down to a decision node, right? You come down to a decision node, and then in the decision node, you have another decision to make, right? If the study hour is greater than 5 hours, let me just add HR to make it hours. So there's some few decisions that you want to make. So is sleep hours I'm just gonna put HRS. Is sleep hours greater than 6? Is the student sleeping? That's to show you how sleep is so crucial to maintain a healthy brain and everything. So, is the student sleeping sleeping hours above 6? Right? If it is a yes, you have another decision node. So before we proceed to this, let's have another leaf node right here. So if the study hours is greater than 5, then you come down to this decision node. And if the study hours is not greater than 5, meaning less than 5, you have a node, right? And then you have a leaf node. This is where everything ends. As soon as it reaches this no, it ends here, right? So automatically we are going to fail the student. Fail, right? And then we call this a what? A leaf node. Don't worry, I'm going to explain these things in a nutshell. Just give me some time. So okay, let's come back to our decision node here. So if the sleeping hour is greater than 6, we are going to have another decision node right here. So this is called a decision node. A decision node is basically a node that has a decision, that has maybe a question to it, right? That is split into 2 based on yes or no, as simple as that. So decision node, right? Don't mind my handwriting. So we have another decision node. If the sleeping hours greater than 6 is yes, and then we are going to ask a question: is social activity is equals to low? Social activity equals to low. Is the student's social activity low, right? And then we are just going to cycle that as a node, right? If the social activity is low, then if the social activity is low, if that is a yes, then then the student is predicted to pass his exams, because the student is studying more 6 hours, the student is sleeping above the student is studying more than 5 hours, and then the student is sleeping more than 6 hours, and the student is not wasting his time in the clubs, he's having a low social activity, and we predicted the student's performance to be pass, right? And if the social activity so if the student is not having this, if the social activity is high, social activity though, if it is no, that means the social activity is high, right? So if the student's social activity is high, then we are going to have a leaf node. A leaf node is a node where there is no decision to split, right? That's the end of the tree. So if the social activity is high, that means we fail the students. It's a fail. It's predicted to have a fail, right? And we have a decision node right here, so definitely it should have a no, right? Let me just make that blue. And if the sleeping hours is if the sleeping hours is not greater than 6, which is no, and then there's another leaf node right here, which is definitely going to fail the student. As simple as that, fail. So this is actually an experiment, I believe. I don't know if it's either done in Stanford University or no, but there's a dataset available for that, which we're going to cover in a nutshell. It predicts a student's performance based on their study hours, based on their sleeping hours, based on their social activity. It predicts the student's performance. So if this student is studying more than 5 hours and is sleeping above 6 hours, and he or she is having a low social activity or social interaction, the student is predicted to have a very good performance. And if the student is not studying more than 5 hours, we don't even have any decision to make about that student. That means a lazy student. Automatically the student is going to fail, and this brings us to the end of this node. So which is a leaf node, as simple as that. So we can call since this side of the tree is having this tree decision, we can call it a sub tree as well, a sub tree. As simple as that. So the key takeaway here is the root node, which is the main entry point, which is the root node, right? And then the end point is called a leaf node. A leaf node is a node whereby there is no any invitation to split like this. So that means it's a leaf node. And then if there's a node with below the root node that has a decision boundary, we call that what? A decision node. So this is also called a what? Since it has two leaf nodes, it's called a what? Decision node. As simple as that. So just take your time and understand this. If you take your time and understand this, it's actually very simple, right? It's actually very simple. So let me just go ahead and I think we've had enough of explanation. I think we can just go ahead and see move on to the next. Let me just move this aside and draw a boundary. So the next thing that I want to talk about is a lot of my beginner students ask me, why do we even use decision tree? And sir, I don't even know when to use a decision tree. So it's actually very simple. You use a decision tree when you want to explain when to use, right? It's actually simple when you want to clearly explain decisions, right? When you want to clearly explain decisions in your model, and then when you have a data that contains both numeric and what? And categories, which we are going to see in a nutshell in the student data categories, right? And then when you also have a non-linear relationship between your data. For example, inside in our linear regression, there's a linear relationship between house prices and the size of the house, right? So when you have a non-linear relationship between your data, that is when you use a decision tree, right? Non-linear relationship. Non-linear relationship. I hate writing, honestly speaking. I love typing. So when you have a non-linear relationship, that is when you use a decision tree, right? So why do we even use, let me just draw a line across that. Why do we use a decision tree? Why? So the decision trees, honestly speaking, why? Decision trees are basically very easy to understand, as you can see from the illustration that I just drew you. Decision tree, they handle categorical data and numerical. Categorical, I told you in our previous class, categorical like yes or no, right? Like binary yes or no category, right? And numerical data, which is in numerical number data, right? Numerical data, which is basically numbers, right? It handles both categorical and numerical address, and it's good for classification. These trees are good for classification. Please, if I were you, I'd be taking notes. Is good for a classification problem. Let's say you want to classify the iris data set, or maybe you want to classify it can be used for the Titanic data set as well, right? So you can also use a decision tree when you don't require data to be scaled, right? When you don't require a data to be scaled, you just want to make decision out of it. When you don't require a data to be scaled or to be scaled, right? And when you want to show some features, so the importance of some features, right? Feature importance. So if you want to know more about decision trees, you can just go to a Scikit-learn Scikit-learn website, and then you can read about it, right? We can go on and on and on and on, but I believe these are the key major ones that I can think of. But if you want to dive deeper, just go to the Scikit-learn library, just Google Scikit-learn, and then go to the website, and then there you can have in-depth explanations of these of these things, right? So there's one thing that I want to show you guys about decision trees. Let me just move this blackboard aside. There are some things that I want to show beginners. So for example, there is this what we call an entropy. I don't know, maybe you did this in your secondary school. Entropy, right? Entropy. Please, you have to understand this, honestly speaking. So what is entropy? Entropy is basically the measure of disorder or impurity, imbalance, right? Disorder or impurity. Disorder, in other words, imbalance, or what? Impurity, right? Let's say, for example, we have what? We have a low entropy. Low entropy. I'm doing this just because I don't want a situation whereby you're seeing entropy and then you have no idea what an entropy is, and you've gone through my decision tree course, right? So that's why we're doing this entropy. So we have low entropy, and then we have high entropy. High entropy, right? So let's break this down. It's very simple. Low entropy is when a data is mostly one class. For example, when a data is mostly one class, that's low entropy. And let's say, for example, in a student data set, let's say, for example, we want to predict either a student passed or failed, right? Let's say, for example, okay, let's say we have 10 students that pass according to our prediction. We have 10 pass, and let's say, for example, one fail, right? So if you take a look at this is actually a pure node, right? This is a pure node. We call this a pure node, right? For example, you have pass, right? You have pass, and then on the other side of the leaf node you have a fail, right? This is actually a very, very clean node, right? This is a very pure node. And then this is a low entropy node, and then we have a high entropy. High entropy is when the data is mixed evenly. It's very difficult to make decisions. By me looking at this, you can simply draw a tree whereby we have 10 students that passed and maybe one student that failed, right? And then here on the high entropy node, let's say, for example, data is mixed, right? We have data is mixed evenly, right? So for instance, let's say we have e.g., let's say we have 5 students that passed, and then, for example, and then 5 students that failed. So as you can see, we have a very poor decision boundary here, right? There's no good decision right here. Here you can clearly make a decision that on average you can write something like 90% of the student pass, right? So but here you have a very, very poor decision boundary, right? So it has a word, impure node, because they are mixed evenly, which is very bad for a decision tree, honestly speaking. Impure nodes. So pay attention to this low entropy. If you want, you can go ahead and research more about it. Low entropy node and high entropy node. So the goal of decision tree, right? The main goal of a decision tree, right, is to reduce this entropy, to reduce the entropy, right? To reduce the entropy. Pay attention to this, please. Is to reduce the entropy by asking good questions, right? By asking, right, good questions. Right? Good questions, right? Good questions. So this is actually a terminology for that. It's called information gain. Information gain. Right? So the goal of a decision tree is to actually reduce reduce the entropy by asking good questions. And this basically means information gain. So we don't want a situation whereby after going through our decision tree, we are having, let's say for example, 5 pass and 5 fail. Right, that's a very impure node. But in a pure node, it's a situation whereby you have 10 fail and 1 pass, or maybe 16 pass, or maybe 2 fail, something like that. Right, that's beautiful. So, and there's a mathematical equation for that, though I don't want us to be like we did in the last class where we did some some intermediate equations. Actually, I wanted us to do this equation, but because of network and the rest, we're not going to be doing that. So, but I'm going to just show you the equation. If you want to go down deep into the rabbit hole, this is what we call entropy, the equation for the entropy for having a pure node, right? This entropy is actually equals to minus P1 multiplied by what? By log 2, then open bracket P1 minus P2 multiplied by what? Log 2, open bracket P2. If you want to deep dive into the rabbit hole, this is your equation for entropy. And let me just expatiate on that. It's actually very simple. I don't know, whenever I say very simple, if you guys are actually finding it to be very difficult. So for example, let's say for example, P1 is actually the proportion of class 1, right? P1 is actually the proportion of the first class of class 1, and then P2, this P2 is actually the proportion of class 2. The proportion of class 2, right? So the entropy, as you can see, the equation calculates the proportion of class 1 to class 2. The proportion is the same, like 5 over 5. That's a very high entropy. We don't want a situation like that, right? So these are the limitations of a decision tree, because if you have a high entropy in your decision tree, you're going to have a very bad prediction. So try as much as possible to limit this entropy. Don't worry, you're going to cool. So I just ran Jupyter Notebook as usual, which started the Jupyter server. So this is going to open this Jupyter Notebook directory, which is in the current directory where I run the Jupyter Notebook. Nice. So I'm just going to go ahead and click on new and then Python IP kernel. So this is going to allow me, this is going to open a new tab in my browser with a new untitled notebook. So that's going to take like a second to load. The first thing to do is just to go ahead and rename our notebook. So I'm just going to name my notebook decision_3, and then I'm just going to press enter. So without any further delay, the first thing I'm going to do, I'm just going to go ahead and import my import pandas as PD as usual. I'm just going to go ahead and import matplotlib.pyplot as PLT, and then I'm just going to go ahead and import Cbon as SNS, and the next thing that I want to do is to, as usual, to print imported successfully, something like that. So I'm just going to go ahead and shift enter. So this is going to import all these libraries into our notebook. Beautiful. So the next thing that I want to do is I want to check if I want to import my dataset. So the next thing to do is load dataset, and you guys already know how to do that. df is equals to today I'm not going to be using df because a lot of people thought that we always name our dataset df. This is just a convention, but you can as well name your dataset. Is a variable actually, so I made a mistake. Cbon is actually born. That's the point of adding the print statement. So I'm just going to go ahead and say data is equals to pd.read csv student student underscore data.csv. So the next thing to do is to print the head of my data, print data.head, to see if my data is actually imported successfully. I don't know what's wrong with my PC. Let me just go ahead and close some few tabs to see if that is actually making my PC to slow down. Don't save because I want to save that. So yeah, let me just run that again. Yeah, let's just give that a time to load. So the next thing to do is I want to check for nulls in my data set by using the df.info. So I'm just going to say data.info, and then I'm just going to do shift enter. So info data.info is not defined. Why? That's because my student data has not been read. So I don't know what's wrong with my PC. It's kind of slow. So let me just do data.info directly, data.head, student data.csv. Okay, we are having an error. That is actually normal that we are having this error. So let me just go ahead and check at the name of the data set. So students data.csv, that's student data.csv. So let me just scroll up and add an s to it, students data.csv. Beautiful. So as you can see, we have some few columns on the data sets, which is so amazing. And let's go ahead and make sense out of our data set. We have what? We have the study hours, we have the sleep hours, we have the social activity, we have the exam score, and then we also have the pass as well. And if you pay close attention, the study hours is actually a numeric data, and the sleep hours is also a numeric data, but the social activity is actually a categorical data, right? It's actually not a numeric data. It's either high or low, right? Sorry, we also have a medium. So, and the exam score is a numeric data as well. And then we have the pass, which is purely categorical. It's either a yes, either the student has passed. Based on these features, we are going to be predicting either the student has passed or the student has failed. Beautiful. So I'm just going to run this data.info, which is going to give me some information about my data. As you can see, we have 300 data points, and there's no any null value in our data points, as you can see, which is cool. So this eliminates the need to fill our data with null values, right? So this eliminates the need to actually fill null values. So the next thing to do is I'm just going to go ahead and visualize my pass and fail to see the ratio of student that pass to the ratio of student that fail. So I'm just going to visualize that my pass and fail, which is actually my target. So visualize pass and fail. So that's actually very simple. So just sns.count plot, because I'm just going to be counting the number of students that pass versus the number of students that fail. Pass the x as the pass. I believe pass is capital letter, and then I'm just going to pass the data as this data, right? This data, simple. So I'm just going to go ahead and press shift. Not yet. I'm going to add title, plt.title to my chart. The title is going to be class distribution, right? Cool. So the next thing to do is to plt.show, and then finally I'm just going to shift enter and see, right? So if you take a look at our our class distribution, by me looking at it, we know that almost 200 students passed, and almost 90 something students failed actually. So this gives us a little bit of insight on our data even before we start making predictions. So the next thing I want to do is I want to show you guys a pay plot. I don't know, maybe if we have done that in the past. So let me just go ahead and do that to see if there are some correlation between our data points. So p plot. So it's actually simple. Just SNS. It's just a one line. SNS is pay plot. and then you just pass your data, and then this is what we call hue, and then my hue is going to be pass, right? The pass column, pass, right? And then I'm just going to add it PLT to show to that. So let me just explain some things to you guys. What is actually happening here? Let's take a minute to understand some things here. So this people, what it actually does, it shows some relationship between your data, right? It actually shows you some relationship between your data, which is kind of like cool, right? So for example, if you take a look at what is actually happening here, the hue is basically saying I want you to color these data points based on either the student has passed or failed. So that's the hue, that's the criteria for the coloration, right? If the student has passed, it's going to be a different color, and if the student has failed, it's going to be a different color. So if we pay close attention to that, we can see that we actually have a correlation between our exam score versus our study hours. But between exam score and sleeping hours, yeah, there's actually a correlation, but not that more. And between sleeping hours and our exam score is actually this does not sorry, between the sleeping hours and exam score, this actually not, there's no any linear correlation between them. If you take a look at the right side of our visualization, you can see that the blue represent that the students have passed, and then the orange represent that the students have failed. So pair plot is basically a grid of plots showing how every pair of numerical variable are correlated to each other. For example, the diagonal shows the distribution of each individual, right? This diagonal shows the distribution of each individual. For example, diagonally here, we can see the distribution of each individual, and then the off diagonal scatter plot compare actually two variables between. For example, as you can see here, we have a comparison between the exam scores and study hours, right? So that is it. And the hue parameter, as I said earlier, it's a parameter that the data points are colored based on that column, right? Based on either the student has passed, or based on this if either the student has failed. So the reason why we use it once again is to see if there's any visual pattern that separate pass and failing students. And as you can see here, there's a positive correlation between there's a visual pattern that separates the two, right? And it's help identify which feature are more useful in making the prediction. So we can see that this feature, which is exam score versus the study hours, is a very nice feature in distinguishing between making prediction for the outcomes, right? Identify which feature is useful in making the prediction. So for example, if most paths are clustered in the top right, for example, if most paths, which is the blue, are clustered in the top right, so that means high study plus high exam score, right? So that means you know that this feature is very important. As you can see, the pass is in the top right for most of the data, even though there's no good correlation in this scatter plot. We can see that the pass is in the top right, pass is in top right, right? That means there's a linear correlation between them. So nice. So the next thing that I want to do is I want to do some feature engineering. Don't worry, I'm just going to do my feature engineering, and then I'm just going to go ahead and explain to you guys. So I'm just going to feature encoding and selection, right? So how do we do our feature encoding and selection? It's actually very simple. So there's actually a function in our library to do that. So encode our categorical variable, right? So encoded data, I'm going to create a variable called encoded underscore data, which is going to equal to pd.getDummies. Sorry, our data is not actually pd, data.getDummies .get underscore dummies, right? .get dummies. Oh, sorry. is actually PD. That's pandas.get dummies, right? It's actually a function built into pandas. So I'm going to pass my data set, which is data. And then the second thing that I want to pass is the columns, right? The columns that I'm interested in, that I want to encode, is actually the social activity. Social activity, right? And I want to drop first. It's going to be what? It's going to be 2. Beautiful. So I'm having an error. Column is actually wrong. It's not column, it's columns. Columns, okay, is equal to, okay, I did not add the equal sign. So why are we encoding the social activity? If you take a look at this social activity, it's actually low, high. There are actually 3 categories, right? We have low, we have high, and we have medium, right? So we want to encode that. By now, you guys should know that machine learning algorithms do not understand categorical data or characters. They only understand numbers. In general, computers are very good in numbers, right? So that is why we have to encode these categories into numbers, right? So after making our categories numbers, the second thing that I want to encode, for example, let me just go ahead and print the encoded data for you to see. Print encoded data. Print encoded underscore data dot head. Well, let me just go ahead and say encoded data dot head. Encoded data dot head. Wow, that's beautiful. So if you take a look at this encoded data, we have the sleeping hours. We have, for example, if you pay close attention to the social activity, we have social activity low and we have social activity medium, right? So the reason why we are not having the social activity high is because if it is neither of the two, for example, you can see that social activity low means false, and the social activity, if the social activity is medium, if both low and medium are false, that means the social activity is high. That is the reason why the encoder refused to add a third column for that. So we know that if the social activity low is false, social activity medium is false, it's definitely social activity high. As you can see, the rest of the data is normal, but we are going to go ahead and encode our target, which is either the student has passed or no. Computers do not understand, machine learning algorithms do not understand this yes or no, so we are going to be encoding that. So the next thing to do is to extract our features, to define our input, to define our input, which is what? Which is the X, and our target, which is Y, small letter Y. So I'm just going to go ahead and convert that to a markdown. Where is it? I'm just going to go ahead and convert that to a markdown. I'm just going to shift enter, right? So as you all know, our X is going to be our input, which is the features. So it's going to be the encoded data without the pass, right? Encoded data dot drop. We are going to drop the answer so that the machine learning does not see the answer. The answer is passed because this is what we are trying to predict, and then the axis is going to be 1. I told you that axis 0 is we are dropping the rows, and then axis 1 we are dropping the column. So in this case, we are going to be dropping the pass column, right? Beautiful. So everything except the pass column is going to be our features, right? And then the second thing is for our Y, which is the target, is going to be encoded data underscore data. In that encoded data, we are only interested in the pass column, right? Because this is actually our target. This is what we are trying to predict, right? So, but we are going to map it. As you can see, the pass is either yes, no, yes, no, right? So we want to map it just like we did in our logistic regression. I want to map this to either 1 or 0, right? So if it is a yes, I want to map it to 1, right? If it is a no, I want to map it to 0, right? So I'm just going to go ahead and do shift enter. If this works, there's no any error. That's beautiful. So the next thing that I want to do is to explain a little bit for you guys. So let's explain some things before we move further. So pd.getDummies, this converts this encodes your data, right? It encodes your categorical data into numerical data, but in this case it converted it into Boolean. But Scikit-learn library is going to understand the tags and then convert this Boolean to numbers. Don't worry, you're going to see that in a short while, right? And then we just printed the encoded data.head to see this. And then the next thing that we did is, for our features in our house price prediction, this X are actually like the size of the house, there is the balcony, is the jacuzzi, and the rest, which are the features. And then our Y was the price of the house that we are trying to predict. But in this, our X is going to be the student study hours, the sleep hours, the exam score, the social activity is either high, low, or medium. And we just drop the pass column. I don't want to just like select all these columns one by one. If we drop the pass column, we get everything here without the pass column. So that's why we just say encoded data dot drop the pass column and then leave the rest, right? And then on our y-axis, on our y, which is a target, we are just fetching the pass column, and then we are mapping the yes to 1, and then we are mapping the no to 0. Beautiful. So the next thing is to split our data into training and testing. Split our data to training and testing. So it's actually very simple. We are going to import a library for that from Scikit-learn dot model selection, model underscore selection. We are going to import train test split, right? Train underscore test underscore split, right? So, and then x underscore train, comma, x underscore test, comma, y underscore train, comma, y underscore test is equals to what we call the train test split function that we just imported, train underscore test underscore split function that we just imported, and we want to pass our data to it. And our data is nothing but our x, which is our feature, and our y, which is our target, and our our test size, the percentage of our data that we want for testing, which is test size, is going to be 20% as usual, which is 0.2, and our random state to enable reproducibility as usual is going to be our random state is going to be 1, right? Random underscore state is going to be 1, right? Beautiful. And then there's what we call stratify, which is going to be stratify y, right? I'm just going to go ahead and do shift enter. So let me just go ahead and explain some concept to you, because I don't want a situation whereby I'm just typing things without explaining. So from Scikit-learn, we're importing train test split to split our data into training data and testing data. And then what we're basically doing here is we are splitting the x, which is the features, right, which is here, and then we are splitting the y as well, which is the target. We are just dividing the data into 2. For example, if we take a look at this data, if you divide this data into 2, it's going to be divided from 0, 1, 2 rows above, and then 3 rows. Let's say, for example, these 2 rows above is for testing the model, and then from row 3, from row 2, row 3, row 4 is going to be used to test the accuracy of the model, right? So that's basically what we are doing. We are just dividing the data into 2. 20% is going to be for testing the model after training, and then we are going to be using the 80% to train the model. And the random state ensures a consistent split, right? Every time the model is running, it's going to ensure that there is a consistent split whenever the model is running, right? And then the stratify, it keeps the distribution of classes consistent in both training and testing, right? And we know that our classes is either pass or fail. We have 2 classes, which is either pass or fail, right? Stratify y, and we all know that our y is just our target, right? So stratify our y basically means keep a consistency during the splitting for training and testing. That's beautiful. So let's create the model. The next thing that I want to do is to create the model, right? Create the model. So I'm just going to go ahead and convert that to a markdown, and then I'm just going to shift enter to have a beautiful markdown. So the thing that the library I'm going to import is that from sklearn.tree right? I'm going to import decision tree classifier, decision tree classifier, right? I'm just going to shift enter that. And the next thing that I want to do is I want to create the model, right? I want to create the model. So how do we create the model? It's actually very simple. Create a variable tree model, and then tree model is equal to what? Is equal to the decision tree model that we just imported, decision tree classifier, right? And then I'm going to pass some values to it. I'm going to pass the criterion. Criterion is going to be entropy, just like we did. I don't have to explain entropy for you. Entropy, we've already done that. And then the next thing that I want is the max depth of my tree. The max depth of my tree is going to be 3, and then the random state is going to be 1 as well. The random state is going to be 1, right? And then I'm just going to train the model tree underscore model dot fit, and then I'm just going to pass my X train, which is my training data, and then I'm just going to pass my Y train, which is my training data for the features. Y train, right? I'm just going to do ahead and do shift enter, which is going to train my model, but I'm having some errors. Entropy, okay, there's no entropy, okay, must be a string, okay. Yeah, entropy is actually a string. What did I do? Okay, entropy. Okay, I made a mistake actually. Entropy is actually entropy. So as you can see, my model is training. So, but while my model is training, let me just go ahead and explain some parameters for you. So the criterion, even though I said I'm not going to explain that, the criterion entropy basically means use more information gain to decide the best split. Is it either low criterion or high entropy or low entropy, right? And then the max depth, this limits the tree to 3 levels to avoid overfitting, right? We don't want a very, very deep tree so that our model is going to be so good and so perfect in our training data, and then whenever we pass it the data that is I've never seen, it's going to fail, right? So that's why we are keeping the depth of the tree very small, because if you take a look at this, we're just having some few features, right? Like study hours, sleeping hours, and exam score, right? So keeping the depth of the tree at 3 is actually nice. And then the random state keeps the result the same each time for comparison, right? So the next thing that I want to do is, my model has finished training. I want to visualize the tree for you guys. Visualize the tree, right? I'm just going to go ahead and convert that to a markdown as well. I'm going to do shift enter, right? Visualize my tree, right? So the simple is actually from Scikit-learn.tree, import plot tree, right? And then the one thing I want to do is the plt.figure. I want to create a canvas, plt.figure. The fixed size is 10 by 16, 16 by 10. Fixed size is going to be open bracket, it's going to be 16 by 10, right? And then I'm going to call the plot tree function that I just imported, plot underscore tree, and I'm just going to pass my tree model, tree underscore model, and then I'm just going to pass the feature underscore name. It's going to be x.columns, right? Because that's our features. And then the class names, class underscore names, is going to be, we know that our class names is either a pass or fail, right? Let me just add fail, comma, pass. Beautiful. And then I'm just going to add field is equals to, I want it to be field. So PLT, the title is going to be decision tree student prediction, student pass prediction, right? So I'm just going to do PLT to show on that. plt.show. So if you take a look at this tree, it has actually three main branches, as you can see: branch 1, branch 2, and branch 3. And it uses entropy as impurity measure. As you can see, we are having entropy in each and every node and leaf as well. And so this is a bit complex for you guys, but I'm just putting this for you guys to see and know that there's something like this where you can just visualize your tree like this. But let me just partially explain things for you guys. And for example, the most significant split, which is the first one, is actually anything that is below 64. We have how many samples do we have? We have 84 fail, and then 154 sorry, yes, we have 84 fail and then 154 pass, right? So this is actually the most significant split. So anything below that is actually anything less than the tree went down to further split. Anything below 64, it went further to split again. Anything below 56, we have 81 fail, and then 24 people actually passed. And it even drilled down further to less than, for exam score less than 49. We are having 61 students passing, and then failing, and only three students passing. And if you take a look at on the right, exam score is less than 64 is pass, less than or equal to 60. Let me take a look at that. Less than 64 is this. Less than 64 is actually false. That means it is greater than 64. That's almost 66, and only one student failing, and almost 134 student passing, right? So that's actually a very good classification. And as you can see, we drill down even further. Anything less than 65, we have only one student failing and then 7 students passing, and the entropy is almost at 0. And if you take a look at this node as well, we have sleeping hours, which is less than 7.5, where we have 20 students failing and 21 students passing, and then we even drill down to 19 students failing, and then 14 students passing, and then we have 8 samples where 1 student failed, and then we have above 7.5 hours sleep, 7 students pass, and then below that we have 19 students failing, and then 14 students are passing for the ones that have sleeping hours below 7.15 hours. So that's beautiful. That's actually cool. This is the key takeaway for you guys. So the next thing we are going to do is to maybe plot, maybe do some what do we call it? Some visualization to see the accuracy of our data. So I'm just going to go ahead and plot some confusion metrics just like we did in our previous class. So add confusion metrics for our data. So it's actually very simple, just like we did in our class, in our previous class. So from Scikit-learn .metrics, I'm just going to import classification report, classification underscore report, and then I'm just going to import confusion metrics underscore metrics, and then I'm just going to import accuracy score to see the accuracy of our model as well. Beautiful. And then C1 is already imported. I don't have to import that. I'm just going to make predictions. I'm just going to market my predictions. Prediction is going to be my Y prediction. I'm just going to make prediction and then compare the prediction with the actual values. So Y prediction is going to be it's going to be the tree model. What's the name of the model? Let me see again. Yeah, it's tree model. So I'm just going to call the tree underscore model, and then I'm just going to pass in the X test to it, and this is going to make sorry, I did not add the dot predict. Tree model dot predict. That's cool. So the next thing that I want to do, I want to see the accuracy, right? Accuracy of that prediction. So the accuracy of that prediction is going to be, we're just going to print that. So print accuracy is going to be accuracy is going to be, what are we going to call it? The accuracy score that we just imported, accuracy underscore score that we imported, and then I'm just going to pass the y underscore test to it, and then the real answer, which is y, the predicted answer. So y test is actually the testing data, and then y prediction is actually the model's prediction. So this accuracy score is going to compare between the actual value, which is the y test, and then the predicted value, which is the y prediction, and then it's going to overall it's going to score the model. So, and then the second thing I want to show is I want to see the classification report. I want to print the classification report like this. Classification report. Let me just do that in the next line, and then I'm just going to put comma, and then I'm going to call the classification underscore report, and then I'm just going to add I'm just going to pass the y test, comma, the y prediction as well, the predicted values as well. That's actually it. And the next thing, the final thing that I want to do is let me zoom that a little bit. I want to plot my confusion matrix. So let me just rename this to something more meaningful. Model accuracy and confusion matrix. Just model accuracy. Yeah, model accuracy. I think it's nice, right? So confusion matrix. So the confusion matrix is actually very simple. So I'm just going to, confusion matrix is equal to call the confusion matrix, confusion underscore matrix, and then I'm just going to pass my y underscore test and what my y prediction as usual. Y predict. That's y prediction. And then I'm going to upload that sns.heatmap, and then I'm just going to pass my confusion matrix, and then the annotation is going to be true. I want some annotation on my data, and then the annote is going to be true, and then the FMT is going to be D, FMT is going to be D, and finally the column map, I want the column map to be, let me see, yeah, this, I think this blue looks nice, right? So I'm just going to choose blue as well, since the Scikit-learn chose blue. The column map is going to be blues, right? That's amazing. So the next thing to do is to add our X label and Y labels and our title, and just visualize the data. So plt.x label, it's going to be the predicted value, and then on the plt.y label, y label, it's going to be the actual value, the actual, right? And then finally I'm just going to add the title to it. Plt.title is going to be confusion matrix, right? That's beautiful. And then finally I'm just going to do plt.show. Wow, beautiful. So we're having a scikit-learn metric. We're having another error. Let's see what are we having. The column map is actually wrong. Okay, why are we having that? Okay, it's cmap, not cpa. It's actually cmap. Yeah, cmap. Beautiful. So now we are having our confusion matrix, and we are having our classification report as well. So let me just go ahead and make sense out of these things. If you take a look at this evaluation and accuracy, model accuracy. Okay, let me just go ahead and correct that as well. Model accuracy and evaluation, right? Model accuracy and evaluation. So if you take a look at this classification report, wow, we are having a 93% accuracy. I hope this is not overfitting, because this is actually very nice. So the classification report is for the fail. Let me see which one is fail and which one is pass. I believe one is pass. Let me see, because you tend to forget these things. Okay, yeah, 1 is pass and then 0 is fail, right? So we have actually two classes. 1 is pass, 0 is fail, and then 1 is pass, right? So if you take a look at this classification report, it's actually nice. So the precision is actually 0.83, and then the recall is actually the accuracy is how many predictions are correct out of all. So the accuracy is going to be, where is the accuracy? Where is the accuracy? Yeah, we have 93% accuracy, as you can see, 93% accuracy, and then the precision is of the of all the past students, how many we actually pass, right? That's the precision. Of all the failed students, how many are actually fail? That's 83% of the students are actually, the model was able to predict them correctly, and of all the past students, it almost 100% of the past students are correct. So the model is correctly predicting for the past student with precision, and 83% precision for the failed student. And then recall is actually of all the past students, how many did we correctly predict? Of all the failed students, we were 100% able to predict all the failed students, and then for the past student, we 90% were able to predict the past students, right? So only 10% error. And then F1 score basically means it's a harmonic mean of the precision, right? That's the F1 score. So we have 91 for F1 we have 91 for no, sorry, for no, for fail, and then we have 95% for pass, right? And then let's go ahead and see our confusion matrix. So if you take a look at this confusion matrix, it's actually just like we did in our last class. You don't have to waste a lot of time here. So let me just scroll up slowly a little bit so that we can have, let me just come down one scroll. That's beautiful. So this is the actual values, and this is the predicted values. So of all our for the failed student, we were able to predict 20 students correctly, and then 0 students incorrectly, right? And then for the pass, we were able to predict 36 students correctly, and then we only made mistake 4 times. So just confusion matrix are actually simple. The best way to actually know confusion matrix, just check them diagonally. So 20 and 36, these are the real values, and then these are the mistakes, right? From the top right to the bottom left, these are the mistakes. So we made 0 mistake for the fail, and then we only made 4 mistakes for the pass, right? That's actually how you simply understand confusion matrix. So with that out of the way, the next thing to do is actually what do we do now? I believe we have already we're almost done. So the next thing to do is actually to just save our model and then call it a day. So I'm just going to say save our model, because we are having 96% accuracy, sorry, 93. There's nothing to add more to this model, honestly speaking, though you can further enhance this model by tweaking some things, but I believe 93%, anything above that is going to be overfitting, right? So I'm just going to import job lib as usual. Import job lib. And then the next thing that I want to do is I want to save the model, right? Save the model. So it's actually simple, just job lib.num, and then you want to pass the name of the name of the model is 3_model, and then the name of the file is going to be student_pass_model.pkl. So this optional, sorry, this is a matter of preference. If you like, you can put anything that you want, but for me it's going to be student pass model. That's the name of the model, right? And then if I run this, I believe it's going to save the model. Let me just go ahead and check the file. Where is the I believe it's in my introduction to Python, which I believe is in my downloads. Very good. So let's take a look at that. Yeah, it's saved here. As you can see, student pass model, which is saved already. So beautiful. So now let's import our model and use it. Import model and make new predictions, right? So the next thing that I want to do, I want to load my model, right? So I want to create a variable called loaded underscore model, and then it's going to be job_lib, which is very simple, job_lib.load, and then I'll pass the name of the model, which is what, which is student underscore pass underscore model dot pkl, right? So this is going to load the model. Let me just go ahead and run that. If I don't get any error, that means the model is loaded correctly. So let me make predictions using a new data that the model has never seen. So this is going to be, I'm going to import numpy. Have I imported numpy? Let me check. I haven't imported numpy. So I'm just going to import numpy as np, in case numpy as np. And then the next thing that I want to do is I want to, let's check the columns. Let me just print something, x.columns. Let me see the name of the columns in our features so that we use that to make predictions. Okay, we have the first thing is study hours, sleep hours, exam score, social activity low, and then social activity medium. Very good. So let me use these columns. Let me use this information to make predictions. So I'm just going to say, let me create a sample data, right? Sample data is equals to, let me create a data frame, pd.data frame is going to be, I'm just going to give, let's say the student studied for 4 hours. The second thing is actually sleep hours, right? Okay. And then the student actually slept for 6 hours, and the student exam score is 70, and then the student social low activity, no, I don't want a low social activity, social medium activity 1. That means the social medium activity is medium. 0 means it's not low activity, 1 means it's medium activity, right? And if both social low and social medium are 0, that means it's social high, right? So I have my sample data already. So the next thing that I want to do is I want to make predictions. So the result is going to be the loaded model. This time we're using the loaded model to make the predictions. Loaded model.predict, right? And then I'm just going to pass my sample data, right? So yeah, I'm having some warning. Yeah, okay. Have feature names, but decision tree was fitted with feature names. Yeah, no problem. This is just a warning. Okay, let me just let me add the feature name so that we make pandas happy, right? So I'm just gonna say columns is equals to x.columns, right? So the next thing that I want to do is to print the prediction. So print prediction is going to be, let me look through the prediction. So let me use list comprehension to do that. I believe we've covered this in our beginner programming class. If we haven't covered that, just go ahead and search list comprehension. So it's going to be fail if the result is equals to 0, right? Else it's going to be pass, right? For R in the result of our prediction, which is this. I'm just looking through this result. If it's 0, that means it's if the result is 0, that means it's pass, right? Sorry, if it's 0, that means it's fail, but else if it's above 0, that means the students has passed. So let's print the prediction and see. Yeah, the students has passed. That means 4 hours. Let me run x.column and see again. So 4 hours study time, and then maybe yeah, let me just come down here and print this x.column because I really want to see the feature names, right? So study hours is 4 hours, as you can see. Sleeping hours is 6, and then exam score is 70. Social activity is medium. So let me just go ahead and change that. Let me make the student is so lazy, he only studied for 1 hour, and then his exam score is 40. 40, right? So let's run the model and see the prediction. It failed. That means the model is working perfectly. So that's gonna bring us to the end of this class. I believe you guys have found this lesson to be so amazing. So if you don't understand any concept, just rewind the video back and front until you understand the concept. If you have any issue, if you're facing any difficulty, just go ahead and reach out to the host in your WhatsApp groups, and then they're going to reach out to me. So I wish you guys all the best. Please practice a lot. Practice makes permanent. So this brings us to the end of today's session. I'll see you guys next week. Bye.